All right, so what we're going to talk about today is we're going to do a brief introduction to a notion known as implicit differentiation. And as a first step in implicit differentiation, one needs to have a working pen, which is why I really should have grabbed this ahead of time. There we go. Here I have a pen that works. So implicit differentiation. Now, how does implicit differentiation work? Well, the idea is, okay, we've got all these rules of differentiation that we have talked about in the past few lectures, right? So we now have things like the product rule and the chain rule that we can use, and we've seen how to do a bunch of different derivatives. Now, sometimes what you will end up with is you will end up with a relationship between two quantities that can be expressed as an equation. But you cannot just solve for one variable in terms of the other variable as a function very easily. An example of this, a really simple and important example, honestly, is the equation x squared plus y squared equals 1. Okay, well, the problem here is, what does this thing represent? This is important because geometrically it is a circle. Remember, this is actually just the equation of the unit circle. That doesn't look like a Y. Okay, the unit circle. Okay, that barely looks like a circle either, but you get the idea. It is supposed to be a unit circle here. Now, the thing is that Y is not a function of X here. X is also not a function of Y here because this thing doesn't satisfy the horizontal or the vertical line tests. So neither of these are going to be functions of the other, but they do obey this relationship. And there are a couple of ways that we can handle this if we want to try to talk about derivatives nonetheless, because we can still ask, if I'm at a given point, what is the rate at which y changes as we change x? That is still a sensible question to ask, right? I could still ask, like, maybe here's where I am. Well, what is the tangent line at this point? You could ask the same kind of question in other situations where, again, you might have some kind of an equation relating to quantities, but you don't necessarily have one quantity given as a function of the other. Now, there are two different ways that we could try to handle this. One of them is we could say, okay, maybe what we can do is we can solve for y as a function of x, and it'll only give us a portion of this graph, but we can then use it on that portion of the graph, and that's okay. So if the point that I'm interested in is somewhere up here, let's say in the upper half plane, I can say, well, y is plus or minus square root 1 minus x squared, and we take the positive option in the upper half plane. So now I do have y locally written as a function of x. By locally, what I mean is, even though this only covers the upper half plane here that I'm trying to illustrate with this darkened curve, that's enough if I'm just interested in what's going on in the upper half plane. But there's another option that we can go through, and that is to use implicit differentiation. The idea behind implicit differentiation is we recognize that y depends upon x, and locally y is a function of x. It's not necessarily globally a function of x, but locally we can think of it as a function of x. And on different pieces of this curve, it might be given by different functions. As we saw, the upper half plane and the lower half plane portions of this graph, we have different equations for y. But in any given region of the plane, around any point, we can think of y as being given by a function of x, except for at places where we end up with a vertical tangent or something like that. So what we can do is we can just treat y as a function of x and realize that if we do that, I can just differentiate both sides of this equation. So I can say the derivative of x squared plus y squared has to equal the derivative of 1. Now, what happens when I do that? Well, in order to take this derivative, the derivative of x squared with respect to x is just 2x. But how do I take the derivative of y squared with respect to x? I need to remember that y is a function of x. It is behaving like a function. So I need to use the generalized power rule, and this becomes 2y times y prime, where y prime is dy dx. And on the right-hand side, I just get 0, because the derivative of a constant is 0. So then what I can do is I can say, well, 2y y prime equals negative 2x. That means y prime is equal to negative x divided by y. Now, this means that if I pick a point on this curve here, I can compute y prime, the change in y with respect to a change in x, by using this formula. The only thing is, it now involves both x's and y's, and that is to be expected because, of course, depending upon where we are on this curve, there's, since y is not a function of x, there are multiple places on this curve with the same x coordinate, and they don't necessarily have the same tangent lines. We would expect that the slope of the tangent up here would be a negative number, but down here with the same x coordinate, it would be a positive number. And that is exactly what we can do in this case. So let's suppose that I want to now find the tangent line to the unit circle at, let's say, radical 2 over 2, comma, radical 2 over 2, and radical 2 over 2, comma, negative radical 2 over 2. So if you go back to that picture, it's really the 2 points that I was sort of sketching there. We've got one point that's in the first quadrant, the upper right-hand portion, and then we've got a second point in the lower right, the fourth quadrant. Well, we already happen to find y prime here. So what we can do is say that the slope at radical 2 over 2, comma, radical 2 over 2, y prime is equal to negative radical 2 over 2 divided by radical 2 over 2. A lot of 2's going on here. Well, this is actually just negative 1. That is the slope of this tangent line at this point. And so what is the tangent line at this point? Well, it's going to be y minus radical 2 over 2 is equal to negative x minus radical 2 over 2. And of course, you can go through and you can simplify this down a bit if you want to and see what this comes out to be. Now, when we do the other point, we're going to get something a little bit different. So maybe let me erase this top portion here and we'll deal with this second point now. So at this point, y prime is going to be equal to negative radical 2 over 2 divided by negative radical 2 over 2. Well, that's equal to positive 1. So the equation we're going to get is y plus radical 2 over 2 is equal to x minus radical 2 over 2. And there's an equation. Again, we could simplify this if we wanted to a bit, but it's fine to leave it in point slope form. So we see here that this time the slope is positive 1. Now, this is not really surprising. This corresponds to intuitively what the tangent line should look like for a unit circle because, let's see if I can sketch a quick unit circle once again. We would expect the tangent line should always be perpendicular to the radial direction. And at the 2 points that we are dealing with, this is square root 2 over 2, comma, square root 2 over 2. Well, this is the line y equals x. So a perpendicular line would have a slope of negative 1. And that is exactly what we found. This point down here, square root 2 over 2, comma, negative square root 2 over 2. Conveniently, I've already got that written right here, so I'm not going to write it again. This line is y equals negative x. It has a slope of negative 1, so the perpendicular has a slope of 1, and that is exactly what we have found here. So we can deal with these types of problems by using this implicit differentiation stuff. The important thing when you do implicit differentiation is going to be remembering that all of your variables need to be treated as functions and thus go through the chain rule, meaning in practice, often the generalized power rule or the general rule for exponential functions and things like this. And when you do that, then, you get the derivative. So let's look at some other examples of implicit differentiation. Let's suppose that I have the following relationship between two variables. Let's suppose that I have x times e to the y plus y squared times the square root of x is equal to 3x. And I want to find y prime. Now, I don't know that I could solve for y here. I honestly, trying to think now whether it would be possible. I don't really think it's possible to solve for y prime here, but maybe somebody could come up with some clever way of doing it. However, what I can definitely do is I can make sure that I find y prime by just differentiating both sides. So I'm going to say, let's take the derivative of the left-hand side and set it equal to the derivative of the right-hand side. Now, if I use the product rule, this is going to give me e to the y plus x times the derivative of e to the y. That's actually y prime e to the y. Then I have to use the the product rule again. The derivative of y squared is 2y y prime. And then we're going to have times x to the 1/2. And then we're going to have plus y squared times 1/2 x to the minus 1/2. And on the right-hand side, we just get 3. So now what I'm going to do is I'm going to solve for y prime. I'm going to isolate every term with a y prime on the left-hand side here. And then I'm going to move everything else over to the right-hand side. So this is going to give me y prime times x e to the y, that's this term here. Then we have plus 2y x to the 1/2. And on the right-hand side, we're going to have 3 minus e to the y minus 1/2 y squared x to the minus 1/2. And then that gives me y prime is equal to 3 minus e to the y minus 1/2 y squared x to the minus 1/2 divided by x e to the y plus 2y x to the 1/2 power. So there we go. We have gotten our derivative. Now, you'll notice the derivative is once again written in terms of both x's and y's. But this isn't too surprising. See, if we write y as a function of x to begin with, then we should get y prime as a function of x. But if y is not given as a function in the first place, if it's just given by a relationship like this, well, then the derivative is also going to depend upon both x and y. In other words, the change in y per change in x depends not just on the x value, but also the y value. So let's take a look at more examples of this. So let's take a look at another one of these examples. Let's suppose that I have something like this. Let's suppose that x times the cosine of y is equal to y times the sine of x. Now, once again, I don't think that I can solve for one of these as a function of the other, at least not very easily. But what I can do, if I want to find dy by dx, is, again, I'm just going to take the derivative of x cosine y and set that equal to the derivative of y sine x. Now, on the left-hand side, the product rule is going to give me cosine y plus x times the derivative of cosine y. I need to use the chain rule. And this is where I think people usually have the most trouble with implicit differentiation. There's this tendency when you look at these problems. Why do I have this on all of a sudden? Sorry, I had to step out of my office for a moment and I forgot to take it off when I came back in. So yeah, there we go. there is this tendency to not remember when you need to use the chain rule. Well, the answer is anytime you're taking the derivative of a variable other than the specific one that's that is the derivative variable, anytime that you're working with a dependent variable, you have to use the chain rule. So the independent variable, that's the one we're doing the derivative with respect to, that's x in this case, that one you don't have to worry about, but that one just works normally. However, all the other variables, in this case y, those I have to use the chain rule. So this is going to pick up a y prime sine y, and it actually also picks up a negative sign, so that makes this into a negative. On the right-hand side, the derivative of y with respect to x is y prime, and then we're going to get plus y cosine x. So at this point, we can move all the y primes to the right and everything else to the left, and that would give me cosine y minus y cosine x is equal to y prime times sine x plus x sine y, and therefore we're going to get y prime on the right, and on the left we will have the cosine of y minus y times the cosine of x, all divided by sine x plus x sine y. So there we go. We have another one of these worked out. Once again, we have y prime. It is in terms of x's and y's, not just in terms of y's. But there we go. That is the basic idea. Now, I'm in kind of a tight schedule today, so this is a super short video, and we're going to come back to this in the next video, but I wanted to at least get something up for you to watch and make sure that you had that. So yeah, sorry, I'm going to stop this here for today, and we'll come back to this, and then we'll also see how you can use implicit differentiation to also find second derivatives, because at this point, I can take another derivative of this thing, or whatever, and we will also see how you can use this to find derivatives for inverse functions. So if I have a function and I know that it has a derivative, then how do I find the derivative of the inverse? Well, the answer is you can use implicit differentiation to do that. So this is going to open up a whole new set of derivatives for us, because we can differentiate things like inverse trig functions. We can differentiate things like logarithms and so on. So we will come to that next time. And like I said, we'll also return to this because I know I didn't do a lot of examples here.